this is a thing that's totally foreign to the control systems community.
Welcome everyone to the Industrial Security Podcast. My name is Nate Nelson. I'm here as usual with Andrew Ginter, the Vice President of Industrial Security at Waterfall Security Solutions. He's going to introduce the subject and the guest of today's show. Andrew, how's it going?
I'm very well, thank you, Nate. Our guest today is Andrew West. He is the Regional Technical Director for Asia Pacific at Subnet Solutions, and he is the chair of the technical committee with the DNP3 users group. And he's going to be talking to us about new security features in the DNP3 protocol. This is a widely used industrial communications protocol, so with new security features, widely used especially for SCADA systems that talk to high voltage substations in the electric sector.
All right, then without further ado, here's Andrew and Andrew.
Hello, Andrew, and thank you for joining us. Before we get started, can you say a few words about yourself and about the good work that you're doing at both Subnet Solutions and the DNP3 users group?
Thanks for inviting me along, Andrew. My name's Andrew West. I have spent nearly 35 years working in SCADA, primarily in the electric power industry. I spent about 12 years working for an electric transmission utility in the substation and control center automation group. Another 15 or so years working for an RTU vendor, where I was the software lead architect for the RTU firmware product. And then maybe 5 or 6 years acting as a consultant. I also spent a couple of years working for a software library vendor in the SCADA space that provides DNP and IEC SCADA protocol libraries. And the last 5 or so years, I've been working for Subnet Solutions as a technical director, and primarily my act there as an internal consultant, keeping up to speed with the standards and also providing services to our various customers. With the DNP Users group, I've chaired the technical committee since 1999, and through that time, there's been quite a bit of change in DNP. Even though SCADA is well established, it's still a moving target. And the biggest changes have been in the cybersecurity space, and that's what I'd like to talk to you about today.
So that's good because, that is our topic, the new security features in the DNP3 protocol. And it's, in a sense, I understand it's a good thing that there's new features because I have the dim understanding that almost nobody was using the old features. But, maybe before we dive into that, can we start with the basics? What is DNP3 and why is it important?
Good question. DNP3 is one of these emergent protocols that came from a vendor, which was Harris, in Calgary, in fact, in the early 1990s, and was put basically into the public domain at a time when most other vendors were very tightly holding their protocols as proprietary. And it was a time also when the industry was clamoring for common protocols, interoperability between different vendors' devices. So DNP emerged in that era, and it's been adopted very widely in the North American power industry to the extent that at the moment, over 88% of North American power utilities are using DNP. So it's got a very wide footprint, and it's very influential in that space. And worldwide, it's used by about 30% of power utilities. So it's got a pretty wide user base.
And in my understanding, the DNP3 protocol was designed for use across long distances, wide area networks, like SCADA applications, as opposed to something like Modbus that was sort of more designed for local area networks. And of course, anytime you're sending information across a long distance, a wide area network, nowadays you need crypto. This is Security 101. I understand that you folks added the, cryptographic capabilities to DNP3 some years ago. What did that first effort look like? And in a sense, why did no one adopt it?
The evolution of SCADA and people's use of it is always a bit interesting. You've correctly identified that there's two significant flavors of SCADA usage, which is the wide area utility style SCADA usage and the local in-factory kind of usage. And the requirements do differ significantly. And I will very simplistically say in-factory tends to require or expect high network reliability, whereas a wide area SCADA, you're at the whims of the telco or some kind of comms provider typically, and you can expect that the communications will fail. And the SCADA system has to manage to survive and recover from those failures in an elegant kind of way. So the different industries have different requirements. Electric power SCADA is typically the wide area style of SCADA. Yes, you're correct that Crypto 101 would say that anytime you put information out on a relatively fragile and open network, you should take steps to secure it. But in the early days of DNP and the early days of SCADA, it was difficult enough just to get systems to work, and that was not the focus of the engineers. And crypto only became something of interest to us in the early 2000s. And so the beginnings of DNP, Secure Authentication, as it's called, started in about 2004, and we released the first version of that in 2007. So that's, halfway through the life of DNP was the first time we actually considered that it was appropriate or necessary, or there was interest even in providing some kind of authentication process for the protocol. And it was partly in relation to emerging market demand, and partly that the technical committee could see that this was a thing that was appropriate to do. And we were concerned about some of the wide area networks, and in particular the radio networks that were used in some industry sectors, and especially in the water industry. There's very wide use of DNP over radio in the water industry.
So that makes sense. I mean, the 2000s, 2001, 02, 03, that was roughly the beginning of sort of the worldwide SCADA security initiative. So it kind of makes sense that, DNP3 would evolve this way. Can you talk about what did the first round of, cryptographic capabilities in DNP3 look like? Are we talking you threw TLS on top of it, or SSL it was called back then, or was it something else?
That really comes down to the beginnings of why it is the way it is. DNP operates, as it was first described and the first documented, DNP runs over serial links, serial RS-232, serial radio, etc. And DNP running over TCP/IP and UDP/IP was only added in 1998. So DNP over IP is a new thing. So we do not depend on an underlying IP transport. So TLS, for example, was not an obvious option because at the time we began the exercise, most DNP installations were running over serial links. So we had a number of things to focus on. One was that whatever we did had to operate equally over whatever media it was, whether it's serial, IP, a mixed channel that transfers between the two. It had to also operate with low-powered devices. So we're talking about the era of 8-bit and 16-bit microprocessors. They don't have a lot of extra horsepower available to spend a lot of time doing complex crypto, and a few other factors. And so the design effort ended up that we were going to add a message authentication code or a hash, an HMAC, onto messages as a signature, effectively. And this meant that it was based on having symmetric keys, and it was a very low process overhead to perform an HMAC across a message and to check the HMAC on the receiving device. But the requirement for that to work was that both devices have to have the same secret key to perform the hashing function. So that's the direction we went in the first round. And we had several attempts, and there were a few false starts. And if you search the web, you'll find a book called DNP Sec. There was basically a publication of someone's PhD thesis, which almost documents the first attempt we had to apply DNP security. And we looked at that very carefully, or that kind of process very carefully, and decided that it was not quite what we wanted to do. So that's where we moved to having a process that had an HMAC to authenticate a message. We were not trying to encrypt or obfuscate the data. We did not consider that the information being conveyed was secret. We just wanted to verify and authenticate that the sending and receiving parties were the devices that we thought should be communicating with each other. So that's where the focus went. And we were very careful to choose algorithms that had open source libraries available that stuck to standard encryption or authentication MAC type functions. We did not try and roll our own because we learned pretty early on that rolling your own security is not typically secure. So that's the direction we took in the first place.
So just so I can properly prepare myself, Andrew, how exactly deep are we going into the crypto side of things in this episode?
We're going a little bit deep. I mean, the whole point of most of these security features in the communication protocol have to do with cryptographic concepts, so one of the differences that Andrew pointed out was the difference between encryption and authentication. Encryption, people kind of know this is what you do when you communicate with your bank. You do not want someone to steal your password. You do not want someone to steal your account number to, use that information to get into the bank and impersonate you. The committee felt when they did the first round of security features on the DNP3 protocol that in that sense, protecting the information, making it impossible to steal the information by encrypting it was not a high priority. Whether a breaker is open or not is not something that anyone can use against you. The focus of the encryption was what's called authentication, which is adding some code, adding a 32, a 64, 128-bit. It's called an authentication code. It's a cryptographic thing, adding this thing to every message so that you could check the validity of the message. So that if someone tampered with the message and said, turn all the lights out, that code is mathematically designed to be very difficult to forge. So it becomes very difficult to forge a message to turn the lights out. So you want to prevent unauthorized control with these authentication codes rather than just encrypt the whole business. So that all sounds, very prudent. You didn't invent your own. You used cryptographic tools that were available, that were, hopefully proven, tools that should stand the test of time because there's a body of, users and investment behind them. And yet, in my understanding, this approach to security in DNP3 just was never widely deployed. Is that understanding correct? And if so, what happened?
As with all things in this space, the answer is a little bit nuanced. So yes, firstly, the basic hashing function was based on AES 128 with the first release of DNP Secure Authentication. And we published that in 2007. After some review, we've tweaked a few things and updated it and released DNP3 Secure Authentication version 2 in 2009, and that became part of the IEEE 1815 standard, which is the DNP3 specification, and that's published in 2010. That process with pre-shared symmetric keys is actually adopted more widely in the water industry than the power industry. And the reasons for that, I think, are invisible to me, but it seems that there's a different level of interest in security in different industry sectors. And it's actually a required component of the DNP3 implementation used in the UK's water industry. So there are some sectors that are deploying that. But the problem we think was faced by people is that essentially for this process to work, you needed to have pre-shared symmetric keys installed in devices. And this is a thing that's totally foreign to the control systems community. And they're quite used to understanding that they've got to configure devices and set them up appropriately when they install them. And if the technician goes out at midnight to replace a device that failed, he has certain things to do, as in loading configuration files or flipping dip switches or whatever it has to be to install a device that needs to be replaced. But then adding some crypto stuff as well is yet another thing. And of course, these keys have to be kept secret. So one of the difficulties is the traditional way of configuring a device is you have a whole bunch of parameters in a configuration tool, and the technician opens the tool, plugs it into the device, and configures the parameters or loads a file of parameters. Those parameters are all visible to everyone who has the tool. And when you go to crypto, you really want to keep the key secret. So you need a different kind of mechanism to install the key so that people can't see the value. You need a different kind of management of the key because someone in the company needs to be able to manage the keys, both the master station or the control center and also the field equipment that it's communicating with, and keep those in a secure manner and distribute them to the people who have then got the responsibility of installing them in the various devices. So it's a whole level of management of configuration data that's totally new and has different requirements. And I think it was a bit complicated for control system engineers who were still struggling just to get systems installed and debugged and working, to then add an extra layer of complexity and a whole bunch of things where they truly did not have the support networks and infrastructure to help them with that. And it's, to some degree, it's the same deal with VPN routers. If you have to install keys in those, you've got to manage that somehow. But our brethren in the IT community are quite used to that, and they've got mechanisms in place for doing that kind of thing. But I think it's just that this is a new thing and it's a new challenge, and the vendors were not all on board understanding the need to keep the information secret, and they provided, as usual, a bunch of different ways of managing the keys that didn't all work happily together. So I think it was quite difficult for utilities to adopt and deploy authentication in the devices.
So that kind of makes sense, but let me make sure I understand it here. I mean, in sort of the modern world, when I set up a website on the internet, I have to set up a private key in the website. I have to buy a certificate for that. I do it sort of to the web server. I have the sense that with this older system that you're describing here, you needed to put a copy of the key, not just in the equipment in the substation, but in other equipment as well, like in the SCADA system as well. Was that part of the problem here?
Yes, that was part of the issue, and I think you've just highlighted two things that were issues. The first thing is, yes, every device that needs to be able to validate or authenticate a message needs a copy of the key. So if you have a pair of redundant master station computers, each of which can talk to a substation device, both of those masters need a copy of that secret key for that device, so that each of the devices that have the key can authenticate that the communication with that device is okay. And if you have some maintenance tools, they also would need a copy of the key if they need to inject commands or to validate the authentication of the messages. So you need multiple devices having a copy of the same key, and you need to coordinate the update of those keys if they get changed. So that's one issue. The other issue is deliberately as part of the design, we wanted to keep this as lightweight as possible. And so the keys are not distributed as parts of certificates. They're just the key value by itself, because we did not want to burden the system with handling certificates, which in the early 2000s was seen as a significant overhead for a SCADA system and were typically much larger than any other kind of data that was being handled within the system or the configuration. So there were two things that drove us away from certificates, and we were only concerned with the private key element that is often conveyed in a certificate.
So Nate, we're doing a bit of a deep dive here. Let's, but it's essential. What we're talking about is authentication, preventing bad guys from forging messages to manipulate the substations. And to do that, we're using cryptographic technology that involves keys. So let's talk about keys for a minute. I mean, a typical small business has how many websites? One, maybe three. For each of those websites, we need to create a if we're going to do secure communications with a website, we've got to put a secret key into the website. We get a certificate. We buy a certificate from the website for the website, and now anybody who connects to the website, the public key infrastructure (PKI) looks after figuring out the crypto, and we can connect to our bank because the bank has one really important secret key in their website. Well, we're talking substations here. We're talking symmetric communications, and PKI is what's called asymmetric. The simpler technology was symmetric encryption. That's what we're talking about here with DNP3. And with symmetric, you have to put a key in each endpoint. And so it's not one website, one key you have to manage. If you've got 100 substations and you've got 4 computers in each substation, that's 400 keys you have to manage. You got to put 400 keys out into your substations. All 400 keys have to be on your SCADA system. They have to be on all of your maintenance equipment. These 400 keys have to be everywhere. If you replace a piece of equipment that's adding your 401st key, yes, you've got to put that key in the new device in the substation, and you've got to put it in your SCADA system, and you've got to put it in all your maintenance devices. It's this key, managing all these keys, that's the issue.
Right. And I know that I only have one set of keys to my house, and I can't even manage that. So what's the solution here?
We're getting into that. I mean, there's a new system that is using the the asymmetric key approach that reduces the number of copies of keys you have to have. So let's listen to Andrew coming up here.
Cyber attacks with physical consequences more than doubled in 2021. For industrial victims, the most common consequences were production outages at multiple sites. Most of the attacks were ransomware. And 2021 saw the first cloud-based ransomware attack. That attack compromised 1,500 businesses in the space of 45 minutes. These and other insights are included in a new threat report, co-authored by Waterfall Security Solutions and the new ICS Strive Industrial Incident Repository. For your copy of the report, please visit icsstrive.com. That's ICSSTRIVE.com.
Okay, and so after a couple of revisions, there was limited adoption, and you folks tried again. What's the new system look like?
We're working on a new thing right now, but there was an interim step partway along that I'd like to mention first. Essentially, one of the issues that people noticed pretty early on was that this pre-shared key idea basically means when I install a device, I put the keys in and I leave them. But to change the key, I've got to drive out to the remote site and update them. And that's a bit of a tall order if I have to do this frequently. So the discussion goes, how often do I need to change the keys? And the answer to those kinds of questions typically starts, it depends. And it depends on lots of factors to do with what your appetite about these things is. And from my point of view, I would tend to let these keys live for years or even the entire life of the product unless I know they've been compromised. And that depends a bit on how securely I know the keys get managed, because if nobody except the administrator knows what they are, they're fairly secure. But if they're in plain text in the maintenance technician's tool, then they're not quite so secure, because if he loses his laptop or some other thing happens, then they could be compromised quite readily. So it's not a simple clean-cut kind of answer. But we recognized that there was a need to be able to manipulate or manage and update the keys remotely, but still in a secure manner. And if I can just highlight what this is like, we still have systems in the world that run on 1200 bit per second serial links. We still have systems in the world where to go and do a maintenance visit, you get in a plane and you fly for 4 hours and then get in a car and drive for 4 hours to get to the site. You don't want to go there just to change the keys. So how long they live depends. But some people definitely recognize that they needed a way to manage the keys centrally and do it remotely. Otherwise, just scaling the deployment up to their full network would have been unmanageable based on the number of devices involved. So soon after publishing the version 2 of Secure Authentication as part of the IEEE 1815 standard in 2010, we embarked upon the extensions for remote changing of the keys, as we considered that this was the next important thing we needed to do. And that work ran over the next couple of years and was published as part of the 2012 update to IEEE 1815. So there is a remote key change process, but for the remote key change process to operate, you need some kind of establishment of trust. So therefore you need a third level of key for which is used to validate the changing of the keys. And that could be done with public key type PKI infrastructure, or could be done again with a symmetric key. And once again, we were concerned about the capabilities of devices, and we required that the symmetric key process was a mandatory implementation if you perform that function, and supporting of PKI in its various guises was optional. And once again, we stuck with the usual standards for the key wrap and distribution of keys that are generally used by the American government, as we considered that those would be acceptable. So there was an interim process, or an interim step, with Secure Authentication version 5 as it became. We had a couple of false starts that were reviewed by various crypto experts who gave us advice about things that should be improved. So SAV5, as we know it, came out in 2012, and that is the current version of DNP security.
Okay, so there is something new coming. Can you talk about what is coming? And maybe, answer first, are we still talking serial, or has the world moved to TCP in these substations?
To answer the second part first, we still have serial. We are still focused on operating DNP over whatever transport might be in place, whether it's serial or IP or whatever the future brings. We do have some of those constraints, so we cannot simply say, well, that was a good try, let's just move to TLS, or let's just move to whatever technology is coming up to secure IP links. So we're still relying on something inside the DNP protocol where there's no other transport. It's just bare DNP on the wire. So that's one of the constraints we had. But we looked at the whole problem the people were facing with managing symmetric keys, the key management, key distribution, installing the keys, keeping them secret. And we identified that we needed to move to something else. And so we've decided to migrate from a key-based process where the keys are used to identify the device and effectively provide the role-based access management for that device. We're instead moving to an authorization model. So it is going to be based on PKI. So all devices, when they're shipped from the factory, will include some factory installed certificate, which could be replaced by the end user. And devices will be introduced to each other on the basis of their private keys from those certificates. And we have developed a fingerprinting way of simplifying the installation of devices without the need for an authority sitting on top. So for systems that don't want to implement a management process for the keys or for the authentication process, we have a verification process that two people, one at the control center and one in the field, need to agree that they are installing a device that is authorized to communicate with its opposing number at the other end of the system. And we have a fairly lightweight mechanism developed for enabling or authorizing that communication to occur based upon the pre-installed certificates and the pre-installed private keys. And this means that no one needs to manage the keys. Nobody needs to see the keys. No one ever knows the values of the keys because it's all based on Diffie-Hellman exchange between the two devices. So that's what the new process is going to do. The next layer of the new process is the remote management of that authentication process. And again, we're not changing the keys. We're not redistributing keys. We are instead going to distribute authentication material. So this is where a system that we're currently calling the authority sits within the utility. And someone at the utility has to identify that certain pairs of devices are permitted to talk to each other. So the control center master station is permitted to talk to an RTU and a substation, for example. And with that communication, it has certain roles that it's permitted to have. And typically a master station has the ability to monitor data and to issue commands, but it doesn't have authority to change configurations or settings and so forth. So the different systems can have different permissions based upon their roles. So we get some role-based access control going on with the authorization. So then we have an authorization process. And again, this relies on certificates. So for that authorization process, we have a mechanism for all of the devices to publish their credentials, their public keys, to the authority. The authority countersigns those credentials and passes them back to the devices in the field. And the devices in the field have to be given the authority's public key so that they can verify that the authority has the right to give them new information to change their authentication credentials or their authorizations. So we have this new mechanism added on top that we're calling the Authorization Management Protocol that distributes authorization to devices but does not change keys. But because we're using PKI, we then have all of the joys associated with PKI and the chain of trust, and the possibility, if a utility wishes to use a certificate authority as well, and have a certificate authority sign the DNP authorities certificates and so forth. So we can have that whole establishment of trust through certificates. Then the authority, the DNP authority, also has the ability to revoke keys in devices in the field if it so desires. So we have a key revocation process. And this means that the authority is now managing the authorization of communication between all pairs of devices and permits the management of role-based access for each of those pairs of devices that are communicating. So it's a whole different way of thinking about security within DNP. And to do this, we've moved the security process from being part of DNP's application layer into a separate layer inside the DNP stack, living just below the application layer. So all of the security messages and the management of authentication and authorization happens below the DNP application layer. And it's a much cleaner way of implementing things, which has the benefits that the vendors should be able to implement it more simply and have a much lower likelihood of having any kinds of bugs introduced as part of that implementation. And there's a lot more detail to it, but it's a pretty fundamental shift, and it's very close to the way that TLS 1.3 operates in terms of its management of credential information. And as part of this change, we're also introducing the capability to add encryption as part of what we're doing. So up till now, we've just added a message authentication code or a MAC as an authentication of plain text data. With the next version of DNP authentication, we also permit encryption of the traffic for those applications that do have a need to keep the information confidential. So it's a bit of a shift in many ways, and we think it will be much simpler to manage because no one has to handle keys, no one has a repository of keys, and it's optional to have the authority or not have the authority. But if you have an authority, it makes your operational life much easier, because if you need to replace a device at midnight, all you need to do is to make sure that that device was introduced to the authority when you bought the device and put it in the warehouse. You then install it in the field, you configure the device, it communicates with the authority authorizes that device to replace the device that previously acted in that same job, and everything goes. And if if a device gets compromised, the authority can declare that device is no longer permitted to communicate as part of the system, and it just gets revoked from the system. And we have the ability for two different masters to talk to a device and basically revoke it from the system and tell the other master to also revoke communication with that device. So we've gone through a lot of the use cases, and we're very focused on how utilities actually use these systems, what the process is to configure them, how you replace something that fails at midnight. You don't want to have the security manager come in just to handle the keys when you need the tech to go out in the field. So we think we've thought through the cases. We think we've got answers for all of them. It's using standard crypto mechanisms again. We're not inventing anything ourselves. We're just applying them in a certain way, and we're especially applying them in a way where simply something like TLS could not be used because we still have the serial link case to worry about. It's complicated, but it's also quite elegant.
So Nate, if I can sort of bring this back to the big picture, PKI is public key infrastructure. It's the infrastructure used on the internet for, pretty much all encryption. This is the way you talk to your banks. This is the way you talk to, Amazon when you're buying stuff. And it's about managing keys. And so in the public key infrastructure, you've got a public key, you've got a private key. The only system in the world that needs to know your private key is your website. So this is sort of the advantage over the symmetric key system that was the first generation of DNP3. In the first generation, you needed the secret keys in the hands of the devices and in the hands of everybody who talked to the devices. And so there was a risk of leakage. Using the new public key system, they can't use the public key system outright because it's designed for the internet protocol, but they can use the main ideas, a lot of the same code as the main public key system on their serial links. And the beauty of it is that the only thing in the world that needs to know the secret keys that must be kept secret is the device itself. And so you no longer have copies of secret keys flying all over the place. This is the advantage in terms of key management over the first gen system. So it all sounds like it's moving in the right direction. How are things going? I mean, you've said that you're expecting a version of the standard to be available in another 12 months. Will people use it? What kind of feedback are you getting from industry?
That's a good question, and we have a little bit of a chicken and egg kind of problem, and I suspect there's also some socialization and education issues here. We have had some interest in what we're doing from people like EPRI and DOE as well, which is interesting. The interest is more in the nature of looking at what we're doing and seeing if that is going to be useful for them. We're not sure yet whether there will be changes in the NERC regulations regarding the communication to field devices. But if, for example, NERC SIP next version turned around and said that something like these features is required on the field SCADA links, then suddenly people might become much more interested. So it's always a challenge to know exactly what the drivers are. I think it's partly the difficulties that people have seen with the previous versions with PreShared Keys and the difficulty with control systems managing keys has been an issue. And this new version is really focused on alleviating that problem and making that whole process much simpler. So I think once people see how it works, it might be a much easier sell. There's also competing interests from other areas. So again, control systems people are not typically very savvy on cybersecurity, and the IT people often get involved and they truly don't understand control systems. They can't see how it's different from any other IP link that they're used to handling with TLS. And if you have a system that has some serial connections, they don't really want to know about that. So I think there'll be more acceptance. I don't know for sure. I really hope there will be, because there's a lot of effort from a lot of smart people going into this. Having said that, there is a equivalent thing happening right now in the European area with the IEC 101, 104 protocols. We're basing all of the work off the same base standard, which is the IEC 62351 Part 5, which is under revision right now in parallel with what we're doing. So there's interest in Europe for this kind of thing as well. It comes down again to the utilities themselves being the drivers of adoption, or alternatively some kind of regulation forcing them to adopt. And the factors that drive that investment are somewhat arcane and difficult to see. But if we don't have anything for them to adopt, they're definitely not going to do it.
Well, this has certainly been educational for me. Thank you, Andrew, for joining us. Before we let you go, is there a thought you'd like to leave with our listeners?
One of the issues that I keep bouncing up against is what drives people to actually do things. So one of the issues in the standards area is that we are focused on doing as good a job as we can, but in the end, it all comes down to what do people agree with or agree to adopt. So fundamentally, we think we're doing some good things here. It would be really great if industry agreed, but I'm not sure that industry is really aware of what's going on and aware of what the options are. So it's great that you're listening to this podcast. Hopefully it's raised a few questions. Go and talk to your vendors about security for DNP3. You might not even have been aware that there was security for DNP. Right now, a lot of vendors have the Secure Authentication version 5 from 2010 available in their devices. And I would encourage you to deploy that with PreShared Keys right now. And don't worry about the remote key change process, because if nothing else, that will allow the devices to authenticate each other right now. And a lot of vendors will have that available for you. So talk to them about that. I've spoken to a number of vendors who've said that none of their customers are asking them for it, so they're not doing it. And the customers are saying, well, we've spoken to our vendors and they're not doing it, so we can't have it. And it's a chicken and egg. If you're not asking for these things, you're not going to get them. And secondly, you have to understand that these are not free. There are costs involved. And with everything in cybersecurity, we have limited budgets. We have to work out which things we're going to focus on, which tools actually meet the various needs we have. And so by this stage of evolution, North American utilities especially have been through the NERC process. They've had to review their systems. They've had to look at where they can be improving their security. And as they go through and do this, they'll probably come to a point where the authentication and security of the field communications is the next lowest hanging fruit. So when you're at that point, look at this. It's one of the options you have. It's a tool. It might be a tool that provides the services you need. And if it is, great, go do it. You'll have heard me say that we're working on a new thing coming out in about a year. Probably it'll take vendors another 12 months to 2 years to actually have it available in products. So we're looking 3 years away before you can buy Secure Authentication version 6 in DNP. Unless utilities go out or the government goes out and says, we need this right now, everyone's got to deploy it by some date, in which case there'll be a radical shift. And I don't really think that's going to happen. So be aware, talk to your vendors, let them know you're interested. That's the first step. And also, be aware that the field communication is one more thing that you might need to secure. And a lot of people just ignore that because all the focus seems to be on the connection between the corporate network and the SCADA system, the control center, because that's where the IT people can see what's going on. It looks like computers talking to computers. Once you get the control center to the field, it doesn't quite look like computers talking to computers so much anymore. And there are some differences there. That's, I think, the most important lesson is wake up, have a look at what you're doing, think about whether this tool would help you with your job, help you secure your system.
Andrew, that was your conversation with Andrew. What did you take away from it?
I love episodes where I learn stuff, and I've learned stuff from Andrew here. I learned that sort of the first class, the first group of security technologies that was added to DNP3, because I knew that DNP3 existed. I was aware that there was some security stuff in there that wasn't used, but I really didn't know under the hood what was that stuff and why wasn't it being used. And it looks like the difference was the difference between symmetric keys and the sort of the modern public-private keys that we see used all over the internet, the public key infrastructure. And so to me, that's a useful learning. A lot of people argue about, is encryption really needed, or is authentication really needed on low-level device protocols? And here are some very concrete examples and experience with that process in a well-known public protocol. So getting sort of the next level detail on that is useful to me as someone who works in this space every day.
All right. Well, with that, thanks to Andrew West for speaking with you. And as always, Andrew, thank you for speaking with me.
Always a pleasure. Thank you, Nate.
This has been the Industrial Security Podcast from Waterfall. Thanks to everybody out there listening.